Hello, everybody. Welcome. I see there are 20 of you already here. So I am going to just wait another minute and then get started. I hope Chapter 3 review is coming along well for you and that you took your practice quiz and then you feel good about all the learning objectives. So the idea of today's study session is to do about half an hour, 45 minutes of review of the concepts. And then after that, I'm going to go over the practice problems with you. So let me know what you would like. Okay. So can I just hear from some of you if that's what you had in mind for today's session? You would like me to go over some of the concepts, or do you want me to delve straight into the problem answering? All right, I hear from Brandon. He says going over the concepts would be great. All right, Dan agrees. So I'm going to go one by one, and then you can let me know where I need to emphasize more or de-emphasize, and thank you for all the feedback. So guys, let's start. The learning objectives for the Unit 3 quiz are learning objectives 1.12, 12 to 20 in Big Idea 1. And the topics that go along with them are electron configurations and the experimental data. So we did a little bit of electron configurations in the previous unit as well, but here the focus is, if you are given a set of experimental data, can you justify an electron configuration based upon that? Mass spectroscopy, a little bit of light and matter, spectrophotometry, law of conservation of mass, gravimetrics, and titrations. So I will spend about 2 to 3 minutes per topic and do a quick review. So in terms of electron configurations and experimental data, these kind of questions could be confusing at times, because remember, the question on magnetic moment in your practice questions was a little confusing because you didn't know what magnetic moment is. Your goal is to find patterns so that you can predict electron configuration. You already know that within energy levels, there are sublevels. Within sublevels, there are orbital. S sublevel has only one S orbital. P sublevel has 3 different P orbitals. D sublevel has 5 different orbitals, and F sublevel has 7 different orbitals. In this context, what you need to remember is para and diamagnetism. Paramagnetism means you have one or more unpaired electrons, and these substances tend to show magnetic property when placed in external magnetic field. And diamagnetism is these substances do not have any unpaired electrons, and if subjected to external magnetic field, they don't show magnetic property. And without giving off much more here, I think this is an easier topic of most others. So I think I am not going to go over any more on it. Can I move on elements, or do you want me to further take a problem and elaborate on this, or do you feel good? Anybody who would want me at this point to elaborate more, please chat me. So Brandon's question, will we have to understand Bohr-Dalton's model? Guys, the thing is, the redesign is a little funky. Redesign says that Bohr's model, you just need to know the very basics, that there are energy levels and the energy of these levels is quantized. Dalton's model has been phased out. So they will not expect you to have prior knowledge of either of the models. Yet with the redesign, they say if they explain the model to you in a question, then they can ask you questions. So do you really need to memorize these models and understand? No. But can they ask you questions? Yes. But they will have to give you what they are talking about. So really where they'll be coming from is they will give you certain written experimental data or numerical experimental data. And based upon that, you will have to either justify a model, or you'll have to say, oh, this is a paramagnetic or diamagnetic substances. So to answer your question, really no need to understand or know these models, as long as you can look at set of data or set of reading in a paragraph and then deduce some things based upon that. So just to clarify again, this is a little crazy part of the redesign. The models have been phased out. However, if they give you written description of the models, then they will expect you to analyze and be able to justify whatever they are asking. Are we good, guys? Okay, so Iris would like me to do a sample problem, and the sample problem I would do is from the practice problems. Do you have the practice problems in front of you, Iris? So I'm going to be doing problem number 3 from the practice problems. Okay, let's do practice problem number 3. Practice problem number 3 gives you a table. And in the table, it gives you the element, it gives you its atomic number, and it gives you a mysterious quantity called as magnetic moment. And they list various elements: hydrogen, helium, lithium, beryllium, boron, carbon, and so on. And atomic numbers are 1, 2, 3, 4, 5, and so on. Magnetic moment varies in values between 0.5, 0. This is not known. This is not known. This is 1. And there are more values, but let's focus here. Now, if this were a new problem, you wouldn't know what this means. What does this term mean? Go beyond that. Go beyond your confusion. Try and figure out patterns. So you are given atomic numbers. So you know number of electrons, right? Which is the same as atomic number. So hydrogen has 1, helium has 2, lithium and beryllium you have to figure out. And then for lithium is given to you 3, 4, boron, carbon 5, 6, right? And magnetic moment given here is 0.5, 0, and question mark, and 1 and 1.5. Now you know it's got something to do with electrons, because that's the only data point they've given you. So if you try and find a pattern, S1, and this is S2, this is S2, P1, right? This is S2, P2, this is S2, P3, that is boron. This is S2, P4. What you see is there are 2 unpaired electrons here, and you don't know its magnetic moment, but here there's 1 unpaired and it is 0.5. With 2 unpaired, it was 0. So maybe that's the pattern. For each unpaired electron, there is a magnetic moment of 0.5. And if you look at the pattern, then this should be 1.5. This should be 1 because there are 2 unpaired, and there are 2 unpaired here. This should be 1 as well. So just don't let the questions frazzle you. Start with what you know and take it from there, and then you'll be able to figure out the pattern. All right, Iris? Okay, I'm going to assume that that was okay. Oh yeah. Okay, I see the chats now. So, Harshit, the idea is I wasn't careful in the data. I did not write all of the data. So the idea here is that when you see one unpaired electron, you got the magnetic moment of 0.5. When there were no unpaired electrons, magnetic moment was 0. And when there were two unpaired electrons, magnetic moment was 1. So you kind of saw that pattern that with increasing number of unpaired electrons, there is increasing magnetic moment. It is the same data, I wasn't thoughtful in writing it. Okay, then I have to write all of it and it's going to take a long time. So the idea there was to figure it out that every unpaired electron is attributing a quantity called as magnetic moment whose value is 0.5. So if you have two unpaired, it becomes 1. If there are three unpaired, it becomes 1.5. And if there are no unpaired, it is 0. All right. So from here, I'm going to go to the next topic, which is mass spectroscopy. And mass spectroscopy is a methodology that separates out the mass fragments by mass. And what happens when you feed a sample in the mass spectroscope, then first of all, your sample generally is in atomic form and is neutral. So you need to convert it to a charged particle. So you bombard it with a bunch of electrons, so they become positively charged cations. Also, you randomly break bonds in whatever you are feeding, a compound or a molecule. So you get mass fragments of different sizes. And after studying what is called a mass spectrograph, you can figure out what all must be in your sample. If you know it was wait, I'm going to take a break. I'm going to read the chats. I have a hard time reading the board. Okay, all right. Everybody can read the board. I tried to put it closer. Guys, should I close the blinds on the other side? Is there shadow on the board? Is the shadow bothering you? I can close it. Just give me a second. Let me go close the blinds. Okay, better. All right. So in mass spectroscopy, you can figure out a lot of things. We'll focus our conversation on mass spectrographs of elements. So when you put a sample of elements on a mass spectrograph, what you have on the x-axis is mass, or mass to charge ratio. We'll assume 1 plus ion formation. So it really stands for mass in AMU. On the y-axis is percent abundance or relative abundance. Percent abundance meaning it's out of 100. Total abundance, if you add all of the isotopes, they exist as 100. Relative is with regards to each other, how much they are. Okay, so if you have an element and you pass it through a spectrograph and you get a spectroscope and you get a spectrograph like that, what all can you tell? Well, if it is an element, you can tell that it has 3 isotopes. You can also calculate its average atomic mass. And you know how you calculate it? Is average atomic mass is mass of isotope 1 times decimal fraction of percent abundance. Decimal fraction means you divide it by 100, and plus mass of isotope 2 times decimal fraction of percent abundance, and so on. You can also figure out if this is a pure sample or not. Because if you know what should be the peaks that you expect, if you get peaks at other places, then you know that the sample is not pure. So that is all you can figure out from a mass spectrograph. Sometimes it is also used for figuring out the structure of substances. For example, the one that I took in the class was N2O, nitrous oxide. There was a debate whether the structure of nitrous oxide is NNO or NON. And when you feed it through a mass spectrograph, what can happen is no bonds are broken. If no bonds are broken, then you will get the mass of this whole fragment, If one bond is broken, the first one or the second, you will get an N fragment here, which you cannot get in this case. So if you get a mass fragment at 28 AMU, or you get a peak corresponding to 28, you know that this is NNO and not NON. So Brandon, that is how you convert the relative abundance to percent abundance, by assuming the maximum to be 100 and then everything else with regards to that. And that is one way of doing it. That is the way that some of the questions on your handout wanted you to do. Another one is to use ratios, is to figure out whatever the total masses out of that, or total abundances out of that, you have this much amounts out of 100, how much will you have? So you'll need to change your percent to relative and vice versa. But remember, for calculating average atomic mass, you do need the percent abundance. If relative abundance is given, that you must change it to percent abundance. Yes, Animesh, the relative abundance is the list of literal number of each mass particle and its abundance. So percent is if you make the whole as 100, what is it? Relative is as they read it. It doesn't have to add to 100. So Sunny asked me, can I draw the graph for the two different structures? So we limit ourselves at APChem to elements. We will not be drawing the graphs for compounds. And N2O is a compound. It gets a lot more complicated. But we could draw a graph for nitrogen. Knowing that its mass is 28, we'll need to first do some research, figure out how many isotopes it has and what are their percent abundances, and then you can draw that. So Sunny, we don't need to draw the N2O graph. So Ashley, to answer your question, we don't know. So what happens is when you feed a sample through through the mass spectrometer, you don't know if any bonds will be broken, or one bond will be broken, or both bonds will be broken. Basically, it is left to chance. It is a random event, and there are billions of molecules in that structure. So if there are billions of molecules, it is highly likely, probability says that some molecules will not be broken at all. In some, the first bond will be broken. In some, the second bond will be broken, and there'll be yet some where both are broken. So you're not talking one or two molecules, you're talking millions of molecules in that sample. So the bonds get broken randomly, and they will because they're constantly being bombarded with the electrons. So they go and give it energy and break the bonds randomly. So probability-wise, it is possible that one or both or none bonds will be broken. So that is mass spectrometry or mass spectroscopy. Next concept is light and matter, and this one has been slashed quite a bit with the redesign. So real relevant thing in light and matter is really the equation C is lambda nu, where remember C is the speed of light, which is 3 times 10 to the power 8 meters per second. Lambda is the wavelength, and its units are in nanometers or meters, and nu is the frequency, and its units are second inverse, 1 over second, or hertz. They are all the same thing. So the product of wavelength and frequency remains a constant, which is equal to the speed of light. And you know that different light photons have different energies, or for that matter, different electromagnetic radiation, quantum will have different energy. And remember, Max Planck found a way to calculate energy of a quantum or a photon. They are one and the same thing, except a quantum of light is called a photon. So using E is equal to h nu, you get energy of 1 photon. And H is 6.63 times 10 power negative 34 joules second. That is its value. I believe it is on your equation sheets. Frequency or the wavelength will be given to you. You will need to change that. If you are converting frequency from the wavelength, make sure wavelength is in meters. And when you put frequency in per second, then E comes out in joules. Sometimes they will ask you, report your answer in kilojoules or so on, so be careful. So these are more mathematical questions that are pretty much related to these two equations. So if you were to combine these two, really you can actually have a third equation, which is E is equal to hc over lambda. So if instead of nu, you're given wavelength, you can either do it separately or just combine it in the equation. So that is light and matter. Any questions around there? So I believe Karina's asking if we need to memorize these. I believe both of these are on equation sheet. I don't have an equation sheet handy. Would somebody just Google the equation sheet for AP Chem and confirm if it is there? I think both of these are there on the equation sheet. I don't think there's any memorization needed. So for tomorrow's purpose, answer is no. Oh, they're on the sheet. Thank you, Animesh. So Karina Animesh says that both of these are on the sheet, so you don't need to memorize any of this. You just need to be able to make sure your units are okay to cancel out. The next concept is spectrophotometry. And on spectrophotometry, we did a lab with blue dye, blue food color, and then we used our standard graph that we came up with to calculate the molarity of the blue dye that was used in blue Jolly Rancher. So spectrophotometry is a technique that uses light to figure out the molarity or the concentration of a color absorbing species based upon Beer-Lambert's law. Beer-Lambert's law says A is equal to ABC, where A is absorbance. Absorbance does not have units. Lowercase a is absorptivity constant, And this absorptivity constant in turn depends upon the wavelength at which you are measuring and on the material of the cuvette. B is path length. What is the width of the cuvette? Generally, it's 1 centimeter. C is the concentration of color absorbing species. Remember, when we took brackets, it means it's the molarity. And also remember the relationship that we came up with, negative log of T at the base of 10 is equal to absorbance. And using this, we can figure out what is the molarity of an unknown substance if we have drawn a standard graph. So what we did to draw a standard graph, on the x-axis, we had molarity or concentration of colored species, generally in micromolar. And on y-axis, we put negative log of T, which was absorbance, and we got a linear regression going through 0 with a positive slope. And now if we had an unknown, you simply stick that sample in the spectrophotometer, get its transmittance or absorbance. And if the values fall within here, then you can just figure it out using the graph. If not, you know, if the graph is going through 0, then your y-intercept is 0. So y is equal to mx plus b. This b is 0. So y is equal to mx. M is the slope. So if you know the slope of the graph and you know negative log of t, which is absorbance, then you can calculate your unknown molarity. Yes, you do get the equation sheet on every single quiz and test. There will never be a testing, both in multiple choice and free response part, where you will not have access to equation sheet. And that is true for College Board as well. Harshit, I will go over problem 8C. Rotational, vibrational, and translational energy. Great question, Madeline. Rotational energy, smallest energy. It's the energy of rotation. Remember, the molecules or atoms are in constant rapid motion, right? So when they are just rotating at their spot, it's called rotational energy, right? It is little bigger than vibrational, which is just vibrating like this, right? This is vibrational, vibrating, right? This is rotational. And translational is sliding past each other, bigger energy, okay? So in terms of smallest to largest amount of energy is associated with these motions, vibrational, then rotational, then translational. So what is relevant to us at our level is when we are talking about electrons dropping from higher to lower energy level or absorbing energy and going from lower to higher, that is related to translational energy. And now 8C. Calculate the energy in kilojoules for 1 mole of these photons. So remember, Harshit, that we did E is equal to h nu, right? This was the energy of 1 photon, right? And if we put h as 6.626 times 10 power negative 34, that is in joules second, and the frequency there was 7.5 times 10 power 14 hertz. This energy will be in joules, right? Because hertz is 1/2, they cancel out, so it'll be in joules. So to turn it into kilojoules, you'll have to divide it by 1,000. But then the energy you will get will be for 1 photon. They are asking for 1 mole of photon. So then you multiply it by 6.022 times 10 power 23, or Avogadro's number, and then you will know how much energy is needed for 1 mole of photons. Is that good, Harshit? Good. So now Dan's question, relationship between transmittance and absorbance, right? So the relationship, Dan, between transmittance and absorbance is negative log of transmittance at base of 10. And this is a mathematically derived relationship. They observed this data in the lab and realized that this is what gives you linear regression. So this is the relationship. There is no more explanation to it as such. This is the relationship that is there between absorbance and transmittance. We know when absorbance increases, transmittance decreases, right? The more something transmits, the less it absorbs. But the mathematical relationship between absorbance and transmittance is negative log of transmittance. Sunny, the energy of photon may not always be given, but you'll either be given the wavelength or frequency, and then using E is equal to h nu, you can calculate the energy. Bhavik, could you please explain question 10 in the packet? Okay, I will. Oh, no. Okay, here. Thank you, Harshit, for that. Can you guys see it? Please keep talking to me because I'm not mindful of the screen sometimes. Okay, question 10 in the packet. Why is spectrophotometric analysis not for group 1 cation solutions, but is appropriate for transition metal cations? Guys, do you remember group 1 metal cations? Do they make colored ions? No. And for spectrophotometry, color is a must because that's when they absorb light, right? So group 1 cations cannot be identified through spectrophotometric techniques because they do not form color ions. But transition metal cations form colors, so you can analyze them and find their molarities using this technique. All right, so I'm going to take your questions in a minute more, but let me now go on to law of conservation of mass. And then the plan is to go over more practice problem than practice quiz. So law of conservation of mass says that mass is neither created nor destroyed, and the application in chemistry is mass of reactants should be equal to the mass of products. And by doing this, this helps us balance the equation. You can balance equation, or if a balanced equation is given, then you can justify it based upon mass or particulate level drawings. And the example I had taken in the class was H2, 2H2 plus O2 gives 2H2O. Guys, remember, to balance an equation, you can only change the coefficients, not the subscript. And when you make the particulate level drawings, you can use any legend. Please share the legend. So if I decide to draw my hydrogens like that, say this is H atom. So then I know what you're drawing. A question. I am coming. Stephen, can you hold your question till I get to titration? Just one more topic before that. So that'll be about 2-3 more minutes. I will answer your question in a minute, Stephen. Okay, so the next one, guys, are there any questions on law of conservation of mass? I thought you guys found it pretty okay in class. So I think I'm going to move on to gravimetrics. Unless if you have a question, then type it. I will look over it. The next topic is gravimetrics. And gravimetrics is when you want to find molarity or amount or grams of something in a solution. But how you find it, because we can see that, is you precipitate it out by adding a certain reagent that will precipitate that species that you're interested in, and then you pour it out and put it through a pre-weighed filter paper. So what happens is this precipitate gets on the filter paper, then you dry and weigh it, and then using stoichiometry, you figure out either the percent purity or you figure out how much was the molarity of the solution in the beginning, or how much, whatever you are trying to find out, how much of that was present in the solution. And that was the concept of gravimetrics. And the last concept is titrations. So in a typical titration, at equivalence point, moles of H plus become equal to moles of OH minus. And generally your acids are like HCl, HNO3, where there's only one H. So instead of saying moles of H plus, you can also say moles of acid become equal to moles of base. And it doesn't end here, because you know molarity is moles per liter of solution. Then you know moles are molarity times volume. So oftentimes you see a simplification of titration written as M1V1 is equal to M2V2. And in a titration, you will know volume of the unknown, you'll know molarity of the standard solution, volume of the standard, and then you can figure out molarity of the unknown. However, the titration that we did, we made our standard solution of NaOH around 0.1 molarity. And we made it very carefully, but because NaOH is hygroscopic and water molecules snuck in there, we now standardized it with KHP. So we took this NaOH and we prepared the burette. We rinsed it with water, then we rinsed it with 0.1 molar NaOH, and we put our NaOH around 0.1 molar in here. Then we took a Erlenmeyer flask and put a weighed amount of KHP, potassium hydrogen phthalate, which is a solid acid, in there, dissolved that solid acid in some water, added indicator, and titrated it to the end point. The goal of this step was to know exactly what is the molarity of NaOH, because we couldn't be sure because of hygroscopic nature of NaOH. Now we know exact molarity of NaOH, which, let's say we got lucky, we got 0.1 molar. Now we already have that NaOH, it is still in the field of urea. We still have that NaOH in here. And now we remove this flask and get a new flask. And in that new flask, we take our unknown acid, which is generally HCl. We took it HCl this time. We add indicator to it. And now we titrate it with standardized NaOH. That is the process. So now let me go back and look at Stephen's question. Why is it that in the key for the titration particulate drawing, standardizing the standard solution has the NaOH in the burette and KHP in the flask, while normally the titrant is of known concentration? So in this case, because if we are titrating against solid acid, Stephen, it is hard. There's no way to put a solid acid in the burette. That is why we took the solid acid. This is still our standard here, right? In this case, what is standard? KHP. NaOH is not standard. We only were about sure, right? We weren't 100% sure. So this really is the titrant. This is the analyte and this is the titrant, right? But we do it this way because here our KHP is solid and there's no way to take it in the burette. Amount of water at the KHP step does not matter because you get the moles of KHP that you are titrating with molarity times volume of the base. So you already know this and you know how much volume of base you are dropping. So the molarity of KHP doesn't matter because you're weighing it out. You can get the mole from the solid amount. So amount of water doesn't matter. Ashley, yeah. Maddie, I'm not sure if you will only be given titration equation with 1-to-1 mole ratio. There might be 2-to-1 or 3-to-1 as well. You just have to pay attention to it and be mindful of which moles are 3. So Ashley's question is, does NaOH continue absorbing water from the air after being dissolved in distilled water? No, it absorbs water in solid state. In liquid, there is the vapor equilibrium. Let's not go there. So the simple answer to your question, Ashley, is no. Dan? So Dan's question, why aren't we sure of the molarity of NaOH? So in class on Friday, I had showed you that NaOH, which is present as solid pellets, the moment you leave it out, it tends to absorb water or moisture from the air and start turning into liquid. So as you're weighing it on the balance, simultaneously NaOH is absorbing water from the air. So you cannot be sure that you have indeed weighed out the amount of NaOH that you think you weighed out because of all these sneaky water molecules in there. Yes, Stephen, that is correct. So can I please do a problem for titration? For sure. Let's do a problem on titration. Which one would you like me to do, Harshit? Do you have a problem in mind for titration, or should I just pick a random one? That pretty much is the end of the concepts session, and now I'll be going over the problems. So let me know what problems you want me to go over, and then I will be doing the practice quiz. So I can take either, practice quiz problems or problems, so tell me which ones you want me to do. So Harshit says none in particular, so I will do 27. Okay, 27 seems a little bit more complicated than the straightforward ones. Do you have 27 easily accessible? 27 says a 32-gram sample of NaOH was dissolved in 250 mils of solution to prepare the titrant. Okay, you made a solution out of that. And then 25 mils of H2SO4 was titrated with the solution. It took 16 mils of this NaOH to titrate to endpoint. What is the molarity of H2SO4? So first things first, we need to figure out what is the molarity of NaOH. It's moles per liter. So 32 grams divided by 40 grams divided by 0.250. Guys, remember, molarity is moles per liter. So if you're given the volume in mils, you must change it to liters. And someone do the math for me and tell me, what do you get? I am not carrying my calculator here. Once you tell me the molarity, then what happens? Let's say this, let's round it. This is about 1, right? 1 divided by 0.25. Around 4, let's just say, okay? Now we know we have to write the equation or it will be given to you. NaOH, H2SO4, so Na2SO4, I will give it to you, plus H2O. So you know 2 moles of NaOH react with 1 mole of H2SO4. So moles of NaOH, right, is equal to moles of H2SO4, but 2 moles of NaOH react with 1 mole of H2SO4, right? We got that from there. And now you will do M1V1 is equal to M2V2. You know molarity of NaOH, you got it here. You know it took 16 mils of it. You have the volume here, and you know you started with 25 mils. So that volume is there. The only unknown is molarity. So the only part, 3.2, thank you, Sunny. So the only thing that's unknown is the volume. So when you solve it this way, you get your answer. Okay. So to Jenny's question, what are the possible errors? There could be many. One error could be a student forgot to rinse the burette with the solution after rinsing with DI water. That brings about dilution of the solution. So they may ask you various things. How would it impact the solution in the burette? It'll be diluted. How would it impact the molarity of the unknown acid? That will be higher. Another error could be there's an air bubble that you don't know, or the student doesn't know. So if there is an air bubble, then you're actually delivering lesser volume than you are reading, right? So if there's an air bubble, this is exaggerated air bubble. It won't be that bad, but you don't know there is an air bubble, right? So for you, you will be reading all this volume that you've dropped, let's say 5 mils. But really, you have only added 5 minus volume of air bubble, right? So you will take larger volume to neutralize the same moles. So you will get a higher molarity of acid. So these are the common errors, Janani, in this. Okay, other questions, guys? Now I am taking your questions either on the practice problems or on the practice quiz. Any questions that you want me to go over, the practice problems or practice quiz? Number 4 on practice quiz. How do you make a calibration curve and what is its purpose? So the calibration curve is made by using a bunch of dilutions of standard solution. So you need to know the known molarities of the colored solution that you want to use and measure its either transmittance or absorbance, and you plot a graph, and that will give you linear regression going through 0. And it is used in spectrophotometry by measuring the absorbance of unknown solution and finding the corresponding concentration. So that was number 4 for question 2. Tell if element sample was impure. So for question 2, how can we tell if the element sample was impure? You will not be. So I will give you, Brandon, that information. I will not ask you for both. You will not be able to tell if these peaks are different isotopes or impurity. Generally, isotope peaks will be closer together, right? Unless it's a half fraction. 7B. Okay, 7A, 7B, then 9. 7A, presence of air bubble. I just went over 7A, guys. If there is an air bubble in the titration, then you will get a, oh, I'm sorry. So this is not titration. I'm sorry, my bad. 7A is about spectrophotometry, presence of air bubble in the cuvette. So your cuvette has colored solution in it, right? You put colored solution. And then you pass light through it. Correct? And when the solution absorbs light. If there is an air bubble in here, light will pass straight through it without being absorbed. So you will get a lower absorbance, and because absorbance is proportional to the molarity, you'll get a lower molarity of the colored species. That is 7A. 7B, fingerprints on the cuvette. So if on your cuvette you have, let's say now you don't have air bubble anymore, there is solution all through it, but there is fingerprint. Fingerprints absorb light. So some light will be absorbed by the fingerprint. You will think that that light is actually absorbed by the solution. So you will get, with the fingerprint, you will get higher absorbance. Because the light that is being absorbed by the fingerprint, you'll think that the solution is absorbing it. So that was 7A, 7B. Then number 9, Karina wants number 9. In an experiment, a student, okay, let's do number 9. In an experiment, a student is given 2.94 grams of mixture. And this mixture has two things, MgCl2, and it has KNO3. To determine the percent by mass of MgCl2 in the mixture, a student uses excess AgNO3. They're interested in mass percent, so they use AgNO3 to precipitate out this AgCl. And they got the mass of AgCl precipitate to be 5.48 grams is AgCl. On the basis of this information, calculate number of moles of MgCl2. So the thought process here is, if from grams of AgCl we get moles of AgCl, that will be equal to moles of Cl, and 2 times moles of Cl are equal to moles of MgCl2. Because in MgCl2 there are 2 moles of Cl, in AgCl there's 1 mole of Cl. So you divide it by the molar mass of AgCl, and then that will be moles of AgCl, and that will be same as moles of Cl, and you 2 times moles of Cl, you get MgCl2. Once you get the moles of MgCl2, you multiply it by the molar mass, so you will get grams of MgCl2, and then you divide it by 2.94, which is the total mass, times 100, and you'll get your mass percent. Sorry, I was on the other screen, so I'm not sure if you guys could see that. Could you still see it, guys, when I was on my other screen? Oh, that's nice. Wonderful. Okay, thank you. So that was number 9. 7A is done, Maddie. How do you determine the optimal wavelength for measuring absorbance in number 6? And what is the reasoning? So optimal wavelength, you figure out by ideally maximum absorbance. You want the results to be most accurate, and because you're measuring molarity by absorbance, you're looking for highest absorbance. But remember, we talked about another criteria, which is for a good sensitive spectrophotometry experiment, the maximum absorbance shouldn't cross a reading of 1, because at absorbance 1, only 10% of light is reaching the detector. So you kind of take both of those factors. You're looking for maximum absorbance under the value of 1 and the corresponding wavelength. So if you look here, the graph that's given to you shows the peak maximum absorbance around 430, and it is below 1. So I'll take any answer, sorry, between 530 and 560. D and E and 22. Okay, so 10D and 10E. Oh, practice quiz. So 10D says, in a second trial, student added too much NaOH. Would this error result in higher or lower molarity? If you add too much NaOH, you will get greater moles and higher molarity, right? Because it's molarity times volume is equal to molarity times volume. If you add larger volume of NaOH and this molarity of NaOH is known, you will get higher moles. And because you took the same volume, like 25 mils or 10 mils, the molarity will be higher. Then E, while doing this lab, another group sees you rinsing the burette with DI water and not with NaOH. They point out to you that you will get a higher value of molarity of HCl. Provide with an argument, do you agree or disagree? That's what I had just said. You agree with this statement because when you have leftover DI water in the burette and you haven't rinsed it. Let's say you put 0.1 molar NaOH in it. Because of all of the water here, this NaOH now will get lesser than 0.1 molar. So what's going to happen? You'll need larger volume of this NaOH to neutralize, but you don't know that you've diluted it. So your molarity will be inflated. So that was for Harshit. Manju, that is number 22, practice problem, okay? You need to make so this is practice problem. Practice problem number 22 says you need to make 50 mils of 5 micromolar blue solution of CV, but you only have 100 mils of 25 micromolar. How would you make this solution? This is a dilution problem. We do M1V1 is equal to M2V2. So we have this much, and how do we want to make? I need to make 50 mils 0.050 liters of 5 micromolar solution, right? And we only have 25 micromolar solution. So 25 micromolar. So what volume of it should we have? So when you do that, this divided by 25, 5.010 liter or 10 ml. So you'll take 10 ml of solution and make up its volume, to 50 mils. And how you do it? You do it using volumetric flask or a graduated cylinder. So you can pour out 10 mils of 25 micromolar solution using a pipette and then make up the volume to 50 mils. That's one way. You can also use preferred ways this. You can also use grad cylinder to take 10 mils, then make up the volume to 25 mils. Either works. So that was Manju's question. Number 8 from practice quiz. That is Harshit's question. Number 8. Consider the particulate level drawing and mole ratios that go with it. Let's do that problem. So this is from practice quiz number 8. And in number 8, you have CH4, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 CH4s. And then you have 1, 2, 3, 4 O2s. 1, 2, 3, 4. And they tell you, so it is CH4 plus O2, and they tell you it forms CO2 and H2O, right? So C, this is C, right? So C, O2, so one O2 is gone, one C is gone, okay? And H2O. So two of these H's are gone and one of these O is gone, right? Now, how many can you make this? When you do this, you realize that you have one more H2O that you can make. You can make 2 water molecules, 1 CO2, right? That is the ratio. And C, H4, 2 and 2, 4. So 2 water molecules, 2 oxygens are gone. So 2 oxygens, 1 CH4, right? One more CH4 and all the 2 oxygens will be gone. So you will have 2 of these and you'll have 4 of these. But remember, law of conservation of mass. What doesn't get used will still remain there. So what you will have is 3 methanes remaining there. These are excess reactant because now there's no more oxygen to react with it. So that was number 8. So how you would be able to determine, Brandon, is how I showed you based upon this particulate level, because they told you you form CO2 with 1 C2Os go and H2O with 1 H2Os go. So by crossing out the particles and seeing what you have remaining, you will know that there'll be 3 methanes left over there. Shravya, in MgCl2, in 1 mole of MgCl2, how many moles of Cl are there? This subscript tells you how many moles. So in 1 mole of MgCl2, there are 2 moles of Cl. Remember, we are not talking Cl2, we are talking moles of Cl. Harshit, you're welcome. Dan, is it okay if we leave units? It is fine. Micromolar and milliliter is fine as long as it is on both sides of the equation, Dan. But sometimes it is only on one side of the equation, then kids slip it. That's why, as a matter of fact, I say that change it to liters. But yes, if they are present on both sides, because the conversion factor would be the same and it'll cancel out, so it's fine to do that. 4, 5, and practice quiz. Do we just talk about? Let me see number 5. No. So number 5 in practice quiz says, how would you figure out, Natasha? So number 5 in practice quiz says, how would you figure out the molarity of unknown? So you will use your calibration curve. And either you can figure out the absorbance of the unknown species, and by extrapolating on the concentration side, you can figure out what's the concentration. Other thing that you can do is figure out the slope. If your value is outside the graph, then figure out the slope, and you know that absorbance is slope times concentration if it is going through a 0. So you will need to use the calibration curve to figure out the molarity of the unknown. Okay, did I miss anyone's questions? You are welcome. You will get a calibration curve on the test, yes. Or if not, you will be given the value of concentrations and absorbance and maybe asked to plot, but generally you're not asked to plot. Yes. Calibration curve really, Shravya, is not even log T equation. What is log T? Negative log T is absorbance. Calibration curve is when you know the standard concentrations or standard solution of the x-axis values, and you are plotting the y-axis absorbance values against it. So you know how much is the absorbance for a given molarity. And then using this graph, you can measure the absorbance of your unknown sample and then extrapolate to find the concentration. That is what is a standard curve. For 7, why would an air bubble increase concentration? Oh, because you're talking about the spectrophotometry lab. Remember, air bubble has air in it, which does not absorb light. So it passes through it. The rest of the solution has colored solution in it. If there was absorbing the light, so your absorbance will decrease, will be higher. I don't have access right now. I don't have my quizzes open. So it might be written type. It might be a few multiple choice. I'm not 100% sure. And no, I'm not making it up. I actually don't remember because I'm making so many. I'm making to your unit 6. So my head is like all confused right now, which quizzes had what. Ashley, if we need to plot the calibration curve. Yes. I don't think that you will be getting to plot a curve tomorrow because the time is limited, but that is something you should know how to do if you're looking to plot the curve. You will be given all the values, you just plug it in your calculator and then it gives you the linear regression. That's correct. The questions are dwindling slowly but steadily. Any other questions? So for number 6, to find the best wavelength, Krishna, there are 2 criteria. You are looking for maximum absorbance, whatever wavelength corresponds to maximum absorbance. But remember, this absorbance should be less than 1. Because typically you figure out the best wavelength with your most concentrated solution. So you want all of the values below 1 because at 1 only 10% of light is reaching the detector. So we don't want any values less than that because you'll get a very inaccurate value. So I'm reading Brandon's question. When doing a titration, the equivalence point is reached when it is pink in color. Well, Brandon, that's actually the end point. Equivalence point is little before the end point. So at equivalence point, actually the moles of acid and base are equal and the solution is neutral at that time. If our eyes could see it, we'll just stop it there. But the indicator, phenolphthalein, does not change color till you add that 1 extra drop of NaOH, so the solution's pH turns basic. So endpoint occurs little after equivalence point. But yes, endpoint is the point that changes when the indicator changes color, and we take it to be the equivalence point because we have no better way. Sunny, if you are given to plot a calibration curve, yes, you will be allowed to use your graphing calculators. You are always allowed to use your graphing calculators on quizzes and exams. Well, not on multiple choice, but on free response. So I don't enforce that in the quizzes, but on the test, you will not be allowed a calculator on the multiple choice. And that is the AP rules, not mine. So I'm just giving you practice with that. Manju, number 17D in practice problems. calculate the I minus. So Manju, could you do part C? Can you confirm if you could do part C? If you could do part C, then I can take you to part D. But if you couldn't do part C, then I'll have to carry it over from top. So I'm just trying to see where you're at. So if you can just let me know. I'll wait for Manju's response. I'll take other questions in the meantime. Can you go over number 10, 13, and 14 in the purple package? Sure, Sherry. Okay, you go, girl. Okay, 10, 13, and 14. Okay, let's see. So 10, I answered that question, Sherry, in this video a little before, but I will repeat again. For number 10, answer is you cannot, it's not, spectrophotometry is not group for group 1 cations because they do not form color ions. They are colorless. Spectrophotometry can only work with colored ions. Hence, it is appropriate for transition metals and not for colors. Okay, 13. How much light is reaching the detector if it is absorbance of 2? Remember, absorbance is negative log of transmittance. So when you put the negative log of 0.01, that comes out to be 2. So you know that only 1% of light is reaching the detector. And number 14. What is the purpose of calibration curve? Calibration curve, as I just mentioned a few minutes ago, is a curve where you plot the known concentrations against the absorbance. So you know what is the absorbance given by a certain concentration. So you get a graph. So when you have an unknown, you just measure its absorbance and find the corresponding concentration. And if your measured absorbance gives you a concentration outside the graph range, you can always figure out the slope of the calibration curve. And you know absorbance is equal to slope times concentration. So you can figure out the concentration that way. But you'll be using the calibration curve for that. Okay, I'm waiting. Manju. Yes, I was able to finish C, but got stuck on part D. Okay, Manju, let's do part D. So part D of 17 says, what is the mass percent they ask you what is the mass percent of I minus. So mass percent of I minus will be mass of I minus over mass of Ki times 100. Mass of I minus is how you get it. You did moles of PbI2 in part C, right? You had 5.12 times 10 power negative 14, no, 4 moles of PbI2, right? And if you look at the formula of PbI2, you know in 1 mole of PbI2, there are 2 moles of I minus, right? So if it is these many moles of PbI2, then this times 2 moles of I minus, right? And then this is I minus moles. And whatever you get here, if you multiply this by the molar mass of I minus, and we take it to be same as I, which is 127 grams per mole, now you know what is the grams of I minus. And then you put that value over here, and the Ki tablet mass they have given to you as 0.425 grams. So you divide this mass that you calculate of I minus here by 0.425 times it 100, and you get the mass percent of I minus in the tablet. So basically from moles of PbI2 times it 2 to get moles of I minus, times it by 127, so you get grams of I minus, divide the grams of I minus by 0.425, which is the total mass of the tablet times 100. Okay. So Manju got that. Krina. In titration, does the shade of pink? Yes, it does matter, Krina. You take the first faintest pink, and if you have gone dark on the pink, then you've overshot it. You'll get higher molarity than expected. Okay, you're welcome, Sherry. How do you know they're color ions? Because they have partly filled D sublevel. Remember, Sherry, any ion that has color must have a partly filled D1, D2, D3, D4, D6, D7, D8, D9. Okay, if they are D5 or D10, then they don't show color because there's not enough room for electrons to jump to the empty D sublevel and then jump back down. When electrons jump from D sublevel to the lower sublevels, that's when they give out radiation in the visible range, so our eye perceives it as color. You are both welcome, Manju and Trina. All right, other questions, guys? You are welcome, Sunny. Welcome, Harshita. No, Natasha, I'm sorry. I read wrong. How are you guys feeling about the quiz? You feel like you're getting there? Yeah? Oh, Ashley, that's very nice of you. Thank you. You're welcome. Excited. Wow, Dan. Yes, me too. All right. What is multi-student video? Who's that? Would you identify yourself? I would definitely go over number 6, no problem. But would you tell me who I'm talking to, whose problem I'm doing? How much transmittance does air have? Definitely lesser, Krishna, than a colored solution. So air has lots of transmittance, right? That is why you see light passes through it. There is scattering of light, which is based upon air particles, but that scattering is still lesser than the absorbance. Colored species will absorb a lot more. Oh, Sarah. Okay, Sarah, number 6. Sketch mass spectra and calculate average atomic mass for following set of isotopes. The most abundant must be set to 100 as a relative abundance and label both X and Y axis. So Sarah, can I tell you how to do this? So here, if you look at this problem 6A for rubidium, they have 2 isotopes, isotope 85 and isotope 87. And they give you the mass number of each isotope, and they give you the percent abundance. Now to change the percent to relative, they said take the higher abundance, so the highest abundance as 100. So we will convert 72.17 as 100. So if 72.17 is 100, how much should 27.83 be? You will be using ratios to get that. Let me repeat again. For isotope 85 for rubidium, you will set it, let me do it here. For isotope 85, its abundance is, percent abundance is 72.17. 0.17. So we assume it to be 100 for relative. And the isotope 87 was 27.83. So we'll have to be using ratios. If 72.17 is 100, then 27.83 will be X. So once you get the relative abundances, then what you're going to do is plot it on the graph. And on the x-axis, you will put mass. So 85, and I'll enlarge it between 86, 87, and then the relative abundance, whatever you get. So 138.6. So 150, 25, so at 38.6, somewhere, 25, somewhere in between here, and that is the 87. So 87 isotope somewhere here, and 85 isotope at 100. That's how the graph will look. So what is concentration, Krishna? So air bubble does not absorb. What are you measuring? This is a cuvette, okay? There is this color absorbing species. Let's say we put a light beam on it, right? This light beam, when it goes through here, let's say 80 of this is absorbed and 20 comes out, right? I'm just putting random numbers. Now, if I replace this colored solution with air, okay, now what's going to happen is what comes out of it is maybe 30, because what was to be absorbed here didn't get absorbed. And that is why what comes out of it will be higher absorbance. You're not measuring transmittance. You're measuring absorbance. Or you're measuring negative log of T. Because of this negative log, if it is more coming out, then your value is higher. All right, Daniel, I see that you got it. Krishna, did I answer your question? So the concentration is not changing of the solution. Air bubble is not mixing. Air is already mixed. It's got nothing to do with liquid concentration. Yes, air has very low absorbance. Air is colorless, right? What is absorbing color? It is the colored species. So if air was colored light, then it'll be different, but it is transparent. So yes, air has much less absorbance. Think of it as a lighter, less dense white glass. Does white glass or prism have a lot of absorbance? Neither does air. No, Krishna. Air will not, lower the absorbance, so its transmittance will be higher. The question is not asking, I think a question is asking, would you get the molarity higher or lower? So you are right in that it will lower the absorbance, but I think the question in there, where is it? Was it on practice or was it on here? Presence of air bubble is lower because concentration, right? It is asking for concentration, Krishna. So if lesser light is absorbed, its absorbance is lower. Its transmittance, the 30 that I wrote, sorry, was for transmittance. So if its transmittance is higher, then its absorbance is lower. And if its absorbance is lower, that means the molarity you'll get, corresponding molarity will be lower. Does that clarify? I got it. So the molarity will be lower. Yes. Yes, and that is the answer. No, I see lower on answer key. Presence of bubble in the cuvette A, it says lower. Light passes through bubble showing lower. Oh, lower absorbance, right? Or higher transmittance. I think answer key is right, Krishna. Check it again. What I see here, the answer for 7A, it says presence of air bubble on the cuvette is lower. Light passes through the bubble, showing lower absorbance. So lower absorbance means lower concentration. Okay, I'm glad. Okay. All right, other questions, elements? So Daniel, you got your question, huh? Okay. Number 6 from practice quiz. Number 6, who asked me that? I think it's Sarah who asked me. Number 6, you're looking for maximum absorbance. And you see that the maximum absorbance for both the peaks is, you know, between 530 and 560, depending how you read the graph. So I gave you a range there. You could write 530, you could write 540, 550. I will take any of those answers. So you're looking for the highest peak. All right, Sarah? Choosing D for number 1 in practice quiz. You're welcome, Sarah Manju. So question number 1. Which of the following statements clearly aligns with the board's model? Electron transitions produce discrete wavelengths, hence discrete energy, providing an evidence for quantization of energy between different energy level. So Manju, to answer this, you really have to read the description very carefully because atomic models have been phased out, but they will give you all the information in the description. So if you look here, it says scientists use data to make conclusions. Atomic emission spectrum of hydrogen gave evidence to build a shell model of atom, much in the way that Bohr did. Electrons receive energy from electricity, from heat, or incident photons. They can be promoted to higher energy levels in the atom. The electron will not stay in this excited state forever. So when the electron relaxes back to a lower energy level, it emits a photon of light. So now they have already talked to you about lower energy, higher energy levels, emission spectrum, shell model, and that the electrons don't stay in the excited state forever. And as they come back to the lower energy, they emit a photon. So based upon that, you can say that there is different energy between different energy level quantization. Or alternatively, I know this description does not tell you about quantization. You can use elimination. So if you look at A, it says the farther the electron, the lesser the chances to leave the orbit. You know that is not true. Electrons are only able to absorb IR radiation and transition among energy levels. That's not true. It doesn't say it there, right? Once excited by an incident photon or heat or electricity, electrons can stay in excited state forever. That is not true either. So by elimination also, D would be your right answer. Yes, for multiple choice, you will need to explain, and I will even take the explanation as by elimination. D is the best possible explanation. That could be an answer. You're welcome, Anju. Any other questions, guys? I'll give you 5 more minutes to mull over the questions. You are welcome, Danielle. Ethan. Number 9 on practice problems. The energy of one of the photons, you just have to plug and chug, Sunny. And the equation for energy E is equal to h nu. So you put the values in there. And h is 6.626 times 10 power negative 34 joules second. And nu is, but they haven't given you nu frequency, but they've given you wavelength. 24 millimeter is 24 times 10 power negative 3 meters. And you know C is lambda nu, so nu is C over lambda. C is 3 times 10 power 8 meters per second. And lambda is 24 times 10 power negative 3 meters. And then you do your math and then plug it over here, and then you get the energy. Ethan, number 2B on the practice quiz. 2B. So what is your question, Ethan? It says, how would you identify? You will just look up your periodic table, Ethan, and you'll find the element whose molar mass is closest to 34.9. My feeling is it'll be Cl. 35 is the molar mass, so that's where you are welcome, Sunny. So that's how you will get it, Ethan. Yes. Thank you, Christian. Yes, chlorine it is. Madhav, will we be given the constant for H and C on the test? Yes, somebody checked. It is on the equation sheet. Well, I think both are on the equation sheet. H you're not expected to memorize, but C you should know. You are welcome, Madhav. So Ashley writes, when we get the ratios of isotope in an element for mass spectrum. Depending who wrote the question, Ashley. So technically speaking, yes, we should get it closer to the ones in nature. But sometimes when I'm writing the question from the scratch, I am not so mindful. I mean, it's not a very nicely written question, but you cannot take that to be a factor. So go with the values given and see what you can make out of that. Karina, for number 12 in practice. Yes, you do use Beer's law, Karina, for number 12 in practice. If absorptivity constant is used, then yes, you will be given the constant on the quiz. Number 486. Sherry, can you tell me which number do you want? Number 4 and 6. So number 4 gives you the percent abundance, gives you atomic mass. They ask you to find element identity. So here is what you do for number 4. In the purple packet, you are given, so you're given a graph. On the x-axis is the mass. Oh, you're actually also given a table. And the table has mass and relative abundance. And the mass is 6, 7, 8, and 100. To figure out the average atomic mass, because if we know the average atomic mass, we can look up the periodic table and find its identity. It is mass of isotope 1 times its percent abundance. So here, if you add both of the relative abundance, it comes out to be 108. So you got to use the ratio. So 100 out of 108 times 8 and 100 out of 100 out of 108. This will be the percent abundances. Once you get that, it will be 6 times whatever this value is plus 7 times whatever this value is. And then when you do that, you get the atomic mass of 6.93 AMU. And now you look over your periodic table and you realize that this is about the mass of lithium. So its identity is lithium. Well, isn't that number 4 on the purple packet, Sherry? Can you please figure out what question you want me to do, Sherry? And then I will be happy to do it. All the questions are numbered. Oh, you meant the titration lab. I don't have that with me. Can you type the question so then I can answer your question? I can always pull it online. Let me go online. Jerry, never mind. I'm going to pull it online. So are you talking 4 and 6? So can you confirm that 4 is the right complete reaction equation for reaction of 0.1 molar acetic acid with NaOH? Is that what you're asking for, Shari? And then number 6, Sherry, is how is it possible to determine when an acid-base reaction is complete when concentration of one of the reactants is unknown? Yes. So the reaction is the same, just like you know that HCl plus NaOH gives you NaCl plus H2O. It's a parallel kind of reaction, except the acid is a little bit more complicated. HC2H3O2 plus NaOH gives you H2O plus NaC2H3O2. Will you be expected to know it at this point? No, but that is the equation. Then question number 6 says, how would you know that the reaction is complete even though you don't know the molarity of one of them? And how you know is when the indicator changes its color. That's when you know that the reaction is done. The first faintest pink that stays for 30 seconds. All right, Sherry? You're welcome. Other questions? So Sherry, please watch the video. I did this problem when I was doing the titration, so it is on there, okay? So basically here, what you're going to do is 32 grams is moles, right? Convert that to moles divided by 40, you get moles of NaOH, and then you will divide it by 0.250 liters, so you'll get the molarity of NaOH. And then you know when you write this equation, and this equation will be given to you, you'll realize that NaOH and H2SO4 react in a 2:1 mole ratio. And you have to multiply then the moles of NaOH by 2, and then you'll get moles of H2SO4. And then you can calculate the molarity of H2SO4 that way. NaOH plus H2SO4. This gives you Na2SO4 plus H2O. So you know 2 moles of NaOH react with 1 mole of H2SO4. So you get molarity times volume times 2 is equal to molarity times volume of this. You know this by dividing 32 by 40 by 250.250 liters. And its volume, you use 0.016 liters. What is the molarity if you used 25 mils? So 0.025 liters. And that's how you can get it. You are welcome. So one thing that's different here is the mole ratio is 2:1 versus 1:1. Okay, I guess I'll wait a couple more minutes. I think most of the kids have their questions answered. Okay, I guess elements, there are no more questions. And I think you guys are, oh. Yes, answer is 2 molar, Sherry, that one. You're welcome. All right, guys, I think that is it for today's live session. Thank you so much for spending your Sunday afternoon with me, and all the best to you for tomorrow's quiz. You are so welcome, Karina. Thank you, guys. Bye. I'll put the timestamp and I will post it on Facebook group. Thank you, everybody. Bye, guys.